asymmetric ciphers. Before we start to talk today, can I remind you guys to turn off your cell phones or turn them down into silent mode? And please enjoy the talk. Thank you very much.
Hello, everyone. I'm happy to be here. I've never been to Black Hat before, and this has been a very, very enjoyable experience. Today, I'm going to be talking about design methodologies for building robust backdoors into secret block ciphers. This is joint work with Youn, who I've done the vast majority of my research with. What this talk is today is it basically surveys 3 papers that I previously published with Modi, and it also touches on very closely related work from other researchers. So when people talk about backdoors, typically these days what they're talking about is either a self-contained malicious software program, or they may be talking about a backdoor that was appended to a binary after it was compiled, or a backdoor that was written in a high-level language and compiled into a program. So these are kind of your typical backdoors. A very interesting class of backdoors is those that are built directly into the theoretical design of ciphers. It's non-trivial to do this. So it's because the cipher also has to behave like a perfectly normal cipher. Takes a key, encrypts plain text data, takes a ciphertext and a key, gives you plain text. So my talk today is specifically going to be about backdoors that are built into algorithms themselves. So this is not a new problem by any stretch of the imagination. This problem caused the United States Air Force a significant amount of concern in the 1960s. So the US Air Force needed to use expensive computing machinery efficiently. So you had batch processing systems that were typically guarded using physical controls. And in order to make efficient use of this expensive machinery, it became necessary to let multiple users use these systems. So these were multi-user operating systems. But the problem was you had different people with different clearance levels all using the same memory. And so this notion of applying physical controls no longer worked. And so as a result, Peterson in turn addressed the possibility of computer subversion in the proceedings of AFIPS conference, where they specifically were talking about malicious software. The actual phrase Trojan horse appeared in the famous James P. Anderson report. And in this report, Anderson identifies the threat of a single agent that operates in a hostile fashion against the organization or agency. And it's noted that such a malicious person can simply install software that bypasses or suspends existing security controls in the system. So the notion of a Trojan horse with respect to computer subversion is older than I am. The data encryption standard was developed by IBM. It was published in 1975. Here are some specifics about DES. It has a 64-bit block size, a 56-bit key size. It was published in the Federal Register in 75. It contains what are called substitution box constants, and it also contains permutation box constants. And it was designed with the threat of differential cryptanalysis in mind at IBM. And even today, the design criterion for the S boxes in DES is still not completely known. As the story goes, DES was developed by IBM. It was shipped off to Washington to be analyzed by the US federal government, and when it came back, the S box values were different. And there are people who speculate that perhaps NSA planted a backdoor into these S boxes that would allow them to decipher any and all ciphertext created using DES. Again, these are all unconfirmed speculations. However, the current wisdom in designing block ciphers has changed. quite considerably. So today, it's common practice. It's considered common practice to do one of two things when choosing integer constants in block ciphers. Either use a cryptographic hash function and hash a seed, and the resulting hash is then used as S-box values. First, it's screened against the known cryptanalytic attacks like differential and linear cryptanalysis. If those S-box values happen to fail, we pick a new seed, we hash, and do it again. And the idea here is that the hash function chooses the majority of the bits in the S-box constants and P-box constants. Again, this is a heuristic. It's not a provably secure method, but this technique was adopted for some of the AES candidates. And again, this is all rooted in demonstrating, insofar as possible, the non-existence of a backdoor in the block cipher. Another approach which is used is to use the expansion of real numbers such as pi and e. Everybody agrees upon these numbers, so if they happen to withstand the cryptanalytic toolbox when used as constants, then where they came from can be accounted for. The digital signature standard, though it's not a block cipher, was subject to some controversy. It was published in the Federal Register in 1994, and it's based on what's called a discrete logarithm problem in a prime order subgroup, and it's related to the Schnorr and Elgamal digital signature algorithms. To review, the digital signature algorithm utilizes three values which can be public: a prime P, a prime Q, where Q divides P minus 1, and Q is 160 bits long, and a value G that has order Q modulo P. So the actual hash function for DSA is quite specifically SHA-1 of the message modulo Q, and the size of the resulting signatures is 320 bits. And so there were a bunch of criticisms put forward when DSA was introduced. One of the criticisms was that the NIST selection process was not public. So the AES selection process was public, and they actually selected among a set of possible candidates. That's not what happened with DSA. Basically, they said, here it is, guys. You know. And there was some discussion on its merits and lack thereof. One of the big criticisms was that originally P was fixed at being up 512 bits long, and people stated this is too small. So NIST responded by letting P be larger, letting P be anywhere between 512 and 1024 at 64-bit increments. And Lenstra and Stuart Haber mentioned that certain moduli P are easier to crack than others. So this is a rather serious issue. And again, in FIPS-Pub 186, a mitigation strategy was introduced to deal with this. This used SHA-1, and the idea was to generate a random 160-bit seed for SHA-1 in an iterative algorithm using a counter value, and the end result is a prime Q that divides P minus 1 and the prime P. And so again, the idea here is that it's SHA-1 that's choosing the majority of the bits in the shared public parameters, not the federal government. So those are examples. Those are the prime examples of the fear of backdoors and how long there has been concern over it. So the cryptographic research community has basically adopted two approaches to casting doubt on proposals for these algorithms. The first approach is to try to discover or reverse engineer a backdoor in an existing cryptographic algorithm. I would imagine quite a number of cryptologists have stared at the S boxes for days, weeks, months, maybe even years looking for a backdoor. And naturally, if you could find one, that would be a huge result of very high significance. However, the other approach, which might not be so obvious, is to say, you know, just ignore the existing block ciphers and say, okay, well, I'm just gonna put on, you know, play the devil's advocate, pretend I'm the NSA, And I'm going to build a cipher from scratch using current wisdom with a backdoor in it, just to see if it can be done, just to see how efficient the result is. This approach would naturally have to use acceptable key and block sizes, standard I/O specifications, and be secure against chosen plaintext attacks for block ciphers and so forth. So it has to look, smell, and feel like a perfectly normal design. And so this approach has been adopted as evidenced by Ridgman and Pernille, Patrin et al., and Youn and Youn, Modi and myself, have taken this approach. So why do we study backdoors in block ciphers? Why do people spend so much time on this problem? Well, we study ways of stealing keys using crypto Trojans so that we can better safeguard them in the future. Note the ambiguity in that statement. We also study ways of stealing keys so that we can establish an appropriate level of faith in black box devices, or lack thereof. I mean, these results, when you take the second approach, they're plausibility results. They say this can be done, so maybe they did it. And this especially holds true when the design of the cipher is classified and it's deployed in a tamper-resistant microchip. Because if you can design a backdoor into a block cipher, even if it's just painfully obvious when you look at it that it's a backdoor, if you can deploy it in a black box environment and classify the algorithm, that casts doubt. So there are some very concrete precursors, or examples, if you will, of block ciphers that were originally secret. There's RC4 from RSA Data Security, which is a symmetric stream cipher with a variable key size, designed by RSA, originally a proprietary trade secret. But as the story goes, I believe it was cypherpunks that got an implementation, reverse engineered, found the code, and spread it all over the internet. Sometimes you'll see this referred to as ARC4, for alleged RC4. Another example is Skipjack. Skipjack was designed by the federal government. It has an 80-bit key size, 64-bit block size. This was originally a secret, but has since been declassified. So some of the questions that you may wonder is, can secret ciphers be trusted for commercial or personal use? Should they be trusted for commercial or personal use? Another motivation, and this one is a far more recent one, has to do with digital rights management. So digital rights management efforts have sought to utilize both code obfuscation and hardware methods to manage digital content. And Bonnet and others described a technique similar to differential fault analysis to cryptanalyze a simplified version of a software obfuscation package. And they also suggested the possibility of using a secret design prior to doing code obfuscation. So these results show that the threat of backdoors and block ciphers, even today, is still not being observed. Okay. The problem hasn't disappeared because we know RC4 and because we know Skipjack. It's manifesting itself in new ways. So the following is the definition of a robust backdoor in a public block cipher. So this is a block cipher that's published in the proceedings of crypto or fast software encryption or something like that everybody knows. So informally, the problem is to design a backdoor with the following properties. User completeness must hold. That means that when Alice sends a message to Bob, Bob always gets it correctly and vice versa. There's also designer completeness, which says that the designer who puts the backdoor in there will always learn plain text. That's a form of correctness of the algorithm. Given enough plain text ciphertext pairs, the designer should be able to read your plain text, and more often than not, that means he learns your key and then simply decrypts. Doesn't necessarily have to be that way, though. Confidentiality is one of the key properties here. Even with the block cipher, it should not be possible to figure out the master key that the designer uses to read all the plain text. So confidentiality must hold even when the cipher is published. And finally, indistinguishability. This cipher must look, smell, feel, and everything like a normal block cipher. It must be indistinguishable from a typical block cipher that a cryptologist would propose. So Richmond and Pernille presented a construction for this. It was cryptanalyzed in Asia Crypt 98. Patarin also presented a construction. It was cryptanalyzed in both Crypto 99 and Eurocrypt 2000. So this is a very difficult problem, very difficult problem. And new solutions for it may very well involve new intractability assumptions that may or may not be related to previous intractability assumptions, and they therefore be questionable. So the following is a definition of a robust backdoor in a secret block cipher. This is quite a bit different. This is a cipher that's declared secret, that's never published anywhere, that's deployed in a tamper-resistant environment. And the completeness definitions here are the same for user and for the designer. However, the other two are different. So confidentiality here, because it's already a secret cipher, confidentiality must hold against what we call the reverse engineer. The reverse engineer has a very, very specific cryptographic role here. The reverse engineer is an adversary who has a lot of money, who is able to breach the tamper-resistant device and learn the entire design of the cipher. Okay, so a robust backdoor in a secret block cipher is only secure if even the reverse engineer can't figure out the master key, and as long as he cannot use the backdoor himself. Okay. However, indistinguishability is quite a bit different. Indistinguishability must hold under black box queries. So here you have a distinguisher that's allowed to make a polynomial number of queries to this chip. He can choose the keys, he can choose the plaintext, he can choose the ciphertext, whatever, but he's polynomially bounded himself, so he makes all these queries, and when he's done, he answers yes or no. I think there's a backdoor or not. Okay, so a robust backdoor in a secret block cipher is only considered secure if even under these black box queries the distinguisher can't distinguish. Now this is a very interesting observation that Matt Blaze, Feigenbaum, and Leighton made. They announced it at the rump session of Crypto 95. And they basically noted that a backdoor block cipher is equivalent to a public key crypto system. And Blaze recently emailed me and mentioned that he believes there's a short write-up on this in the Proceedings of DIMAX at Rutgers University. So this should be in print. And here's the idea, and here's why it constitutes a public key crypto system. So Bob designs a block cipher with a backdoor. He gives it to Alice. Alice chooses a symmetric key K uniformly at random, encrypts a bunch of messages with it, sends it off to Bob. Bob doesn't know K. Alice just chose it randomly and used it. Bob doesn't care. He put a backdoor into it. He uses the backdoor. He reads the plaintext messages. He decrypts the ciphertext. So, and the passive eavesdropper is going to see all these ciphertexts. Well, he doesn't know the backdoor, and he doesn't know K. So it's, all right, so it's not a very efficient public key crypto system, but it does satisfy the definition. So people who sit around pioneering backdoors and block ciphers are actually developing public key crypto systems. I think it's a very interesting observation. So here's a roadmap for my talk. I'm not sure if I'll be able to cover all of these points, but I'll do what I can in the time allocated. The remainder of the talk is going to focus on the 3 papers that I published with Modi Youn. The first paper is a backdoor in a secret block cipher. We call it Monkey. It's an acronym for Monopolizing Keys, which we published in Fast Software in '98. And this paper utilizes 2 key ideas. The first idea is the utility of known plain text in order to extract backdoor information. So we assume that the designer will be able to obtain a number of plain text and corresponding ciphertext under the particular key K that he's trying to break another ciphertext. And also the other observation is the utility of a deterministic asymmetric encryption function in building backdoors. So this would be like RSA as defined in 1978. However, there is a drawback to this result. It doesn't constitute a fully robust, secretly embedded trapdoor with universal protection, because it ends up leaking a single plaintext bit to the reverse engineer in every ciphertext. The next paper is what we call the Black Rugose cipher, named after a trapdoor spider in Australia. So we presented this at ACISP in Wollongong 2 years ago. And this result fixes the problem in Monkey, but introduces a new problem, which is not as bad. And the main observations in this one is that if we use a larger block size, and therefore have more elbow room to display data, can we minimize the exposure of plaintext information to the reverse engineer? And the answer to this is yes. However, and the reason is we use a larger block size and we use data compression, and we compress plaintext when they're sufficiently redundant, and we leave them alone and do normal encryption when they're high entropy. So it uses data compression to fabricate a subliminal channel. But the problem with this result is it's not perfect, because either way, whether it's a sufficiently redundant plaintext or not, it leaks a bound on the entropy of the plaintext, either upper or lower. And then finally, the last result is a paper I presented last year at Selected Areas in Crypto 2004. We call this the Insignis cipher, named after a carnivorous plant. It's commonplace in the design of ciphers to use animals' names and things like that. And this one actually solves all these previous problems, which is kind of nice. But it's really, it's so complicated that even if I put the paper away for a month and get back to it, I completely forget what I've done. So it's pretty involved. Okay, so what is a subliminal channel? A subliminal channel in cryptography has a very, very specific meaning. A subliminal channel is a channel that allows you to send information into or out of a crypto system in a covert fashion. So it's very specifically defined within the context of information leakage in crypto systems. Gus Simmons introduced what's called the prisoner's problem. In the prisoner's problem, there's two prisoners who want to communicate subliminally in the presence of a warden, and the warden will not let them send ciphertext. The warden will let them digitally sign messages. So the problem is to devise a way, not using steganography in the message, devise a way to communicate secretly in the actual digital signature value itself. Simmons came up with a number of ways of doing this, for El Gamal, for DSA, et cetera. And basically the warden doesn't trust them. Trusts them enough to sign stuff, but every time Alice wants to send a signed message to Bob, the warden verifies a digital signature on it. If it doesn't verify, it's not forwarded on to Bob. Okay, so that's the function of the warden. And the reason why I mention this is that the vast majority, actually I can't think of one that doesn't do this, of subliminal channels exploit the fact that the host crypto system that exhibits the channel is a probabilistic algorithm. So in the language of Turing machines, it has a one-way infinite random tape, each containing bits selected uniformly at random, and it reads from the tape and uses those coin flips to produce the output values. And the way these subliminal channels attacks typically work is they use acceptance rejection on the coin flips of the tape. And they'll reject certain sequences of coin flips because they won't allow the backdoor to be exhibited in the output. But when they find a sequence of bits to their liking that exhibits the backdoor, they'll use them and produce the signature or ciphertext or whatever. And this is done in a way that still it's undetectable, even though you're doing this acceptance rejection. You pay careful attention to the resulting probability distributions, and it's still not detectable. This type of acceptance rejection paradigm does not seem to be possible in a block cipher which is deterministic, right? Block ciphers based on Feist-Dell transforms, they don't read bits from the one-way infinite random tape. Right? They're deterministic. You can think of them as being this whopping huge table They take the key, they take the message, they do a table lookup. So in that sense, building a channel into a deterministic encryption function is non-trivial. It's a very non-trivial problem. And in the next two slides, I'm going to be covering the two key ideas, one of which was shared by the other researchers that have worked on this problem, that kind of give you an intuitive explanation of why it should even be possible to leak bits of your choosing in a deterministic function. But this idea here is not to be taken literally. This idea here is just to satisfy your intuition on why this should even be possible. So how can a channel be built into a deterministic function, and how can a channel be built into a deterministic block cipher where the output block is the exact same number of bits as the input block? Right? It seems like there's no space. And the key idea is to appropriate bandwidth by assuming that the attacker will be able to obtain a set of plaintext ciphertext pairs under one key. Now this is just, a cipher is not considered secure unless it's secure even when the attacker has these plaintext ciphertext pairs. Okay, so that's a given. So the basic idea, and again, this is all intuitive, is that this deterministic function is able to communicate with the designer. How? Well, you can think of the ciphertext under key K and the message under XOR as forming a virtual pseudo one-time pad R sub K. So you take, I mean, that's not the way it encrypts, but if you take the message and you take the ciphertext and you XOR them, there's a bit string there that was chosen by the deterministic cipher that could have done some fancy footwork and leaked some bits in there. And again, the attacker, it's assumed he gets access to a plaintext ciphertext pairs, so he can compute this pad for all of them. So there can be information transmission outside of a purely deterministic keyed permutation, which is pretty surprising. The next key idea is the utility of a deterministic asymmetric encryption function. So a deterministic asymmetric encryption function always produces the same ciphertext for a given plaintext. So a perfect example of this is RSA as defined in 78. So the function capital E sub n is the RSA encryption function where you raise the message to the E modulo n. And the other observation is that both the block encryption algorithm and the block decryption algorithm share a common string, a secret string, the symmetric key. So if you supply the symmetric key to the deterministic public key encryption function, you get yet another shared string between the encryption algorithm and decryption algorithm. One that will always be the same given the same input K, plaintext K, but that you can publish. And you can publish it, and it will not compromise K. And this gives you the needed robustness property in the definition of a robust backdoor. So in other words, the encryption function and decryption function both share a common string, the public key encryption of the symmetric key that's used. They can both read from this string at runtime. So the challenge is to somehow display a pseudo-randomly chosen bit in that shared string, that asymmetric ciphertext, in each block ciphertext that's output. And if you can do that, the designer can collect those bits. He's going to get some of them multiple times, but he'll collect those bits. He'll reassemble the asymmetric ciphertext. He'll decrypt it, which only he can do, not the reverse engineer can do. Only he can do, because only he knows the needed private decryption key. And then, boom, he has your symmetric key. So now I'm going to discuss the monkey cipher. Excuse the cheap animated GIF there. I was worried about copyright issues, so I got it off a CD. But this is the monkey cipher, and it wasn't an accident that Modi and I tailored it completely after skipjack. I mean, this was very deliberate. Okay, 80-bit key size, 64-bit block size. And the goal in the monkey cipher is to securely and subliminally leak the 80-bit key to the designer. And basically the way monkey works is it leaks one bit of the asymmetric ciphertext of k in each ciphertext that it outputs. And again, this is a deterministic asymmetric ciphertext, not a probabilistic, doesn't use a probabilistic crypto system. And so I'm just going to give you a quick overview. What is it? I don't need it. I'm all set. So this is an overview of Monkey. I'm not going to give an incredibly detailed explanation of Monkey. It utilizes pseudo-random functions, which is a very specific cryptographic meaning. A pseudo-random function is a function that takes as input a secret input and a public input. And the secret input is sometimes referred to as a seed. And the end result is a bit string that's polynomially indistinguishable from a randomly selected bit string. So this is a very, very powerful cryptographic primitive, and Monkey utilizes it. And the way Monkey works is it's able to leak one bit as long as this bit is a known plaintext bit. So Monkey, quite specifically, leaks secret key information in the most significant bit of each ciphertext block. And actually, it's an interim state of the computation where this bit is located, where this information is leaked. And the way Monkey basically works is when it starts, it does some pre and post processing, but the core algorithm in Monkey simply encrypts the 63 lower order bits, just right away. Just secures them, encrypts them, boom. Now we got to worry about the remaining plaintext bit that we didn't encrypt, and we got to worry about leaking the asymmetric ciphertext bit. And the way that this is done is this remaining bit is encrypted using XOR encryption. And the XOR encryption is of the plaintext bit, a pad bit that's chosen using the pseudo-random functions, and also a pseudo-randomly selected bit in the deterministic asymmetric ciphertext. It's actually 3 values. They all get XORed together, and boom, the result is placed in the most significant bit position. And again, there's pre and post processing because it's necessary to mix the bits together to prevent distinguishing based on statistics. And what happens is the attacker collects these, using the plaintext ciphertext pairs that it's assumed he has access to. He collects these bits from the most significant bit position of the asymmetric ciphertext. So it's under known plaintext. He knows the plaintext. He knows the secret seeds to the pseudo-random function that are in this tamper-resistant device. And he knows the ciphertext bits, and he just XORs them all together. And boom, outspits a bit of the asymmetric ciphertext. And he knows the bit position because of the seed to the pseudo-random function that he knows. And then he just assembles it. And as it turns out, Moni and I didn't put a lot of thought into how many plaintext ciphertext pairs he would need to reconstruct the asymmetric ciphertext. We didn't really think about that one until a referee mentioned in the Black Rugos result, hey, you guys should really bound the running time of the key recovery algorithm for the attacker. And we thought about it, and we realized that the running time is basically an instance of the celebrated problem known as the coupon collectors problem. And so in the coupon collectors problem, I'll give you the simplified example of it. Every time you buy groceries at the grocery store, you get a receipt and a coupon on the receipt. And suppose that there are 100 types of coupons and you want them all. You're a collector. So the question is, how many times do you have to go shopping until you have at least one of each? And it works out to be n log n, where n is the number of types of coupons. So interestingly enough, the attacker, the malicious designer, is a coupon collector, but they're not coupons. They're individual bits in the deterministic asymmetric ciphertext of the symmetric key that he wants to learn. So he needs to collect those. So that's kind of nice. It tells you exactly how many plaintext ciphertext pairs you would expect to need on average. Yes. Okay, again, I didn't give a detailed explanation of the algorithm here. Basically, there are seeds to the pseudorandom functions in it. And once he removes the post-processing layer, he is able to see the intermediate ciphertext, and a huge chunk of that is used as a public input to the pseudorandom function, along with the C that's contained in the tamper-resistant device. And the pseudorandom function actually outputs the bit position that's used. So yeah, at an intermediate stage, the actual ciphertext, part of it is used as the public input to the pseudorandom function. So the pseudorandom functions are a very powerful primitive, and they're used in these attacks. Okay, excellent question. The security of Monkey. So let's discuss the security. Now, the reverse engineer knows more than the average user, so if we can show security against the reverse engineer, we're done, because he has access to the design and the average user doesn't. So let's consider security with respect to the reverse engineer. So the reverse engineer spends a lot of money, busts open a device, sees there's a backdoor, he goes, oh wow, now I want to know everyone's plaintext as well. So he sees all of the seeds to the pseudorandom functions. They're there. Right? So now he has access to that. Well, we need to assume that the reverse engineer gets access to a set of plaintext ciphertext pairs as well. Right? This is just, you can think of this as headers to email, or there are any number of ways of obtaining known plaintext. So the reverse engineer knows these most significant bits in these positions. He can apply the pseudorandom functions just like the malicious designer can. So he can do coupon collecting too. And in fact, he does. And he collects the entire deterministic asymmetric ciphertext. Well, now he's stuck because he doesn't know the needed private decryption key. Okay, so he can't break the whole thing. But since he knows that shared string, the deterministic asymmetric ciphertext, the reverse engineer will be able to discern the most significant bit of other previously unforeseen ciphertext. So he's actually going to be able to learn the most significant bit of every ciphertext produced under that key, which is bad. It's bad, but it's still a very unique advantage that's given to the attacker. There's still 63 bits worth of robustness here against the reverse engineer. So Modi and I refer to this as a quasi-setup. It's almost a secretly embedded trapdoor with universal protection. Setup is an acronym, which stands for secretly embedded trapdoor with universal protection. Yes?
You mean that the people doing reverse engineering will know that there is another channel of information?
Absolutely.
You will say, there's something wrong.
Yes.
But it's stuck because it doesn't have the other key.
That's right. So the reverse engineer has won a mini victory in that the reverse engineer will learn the most significant bit of all ciphertexts. But the buck stops there. I mean, that's, exactly. So we're not claiming that the reverse engineer is not going to know that there's a backdoor there. That's not what this line of research is all about. That is what the line of research on public robust backdoors in public ciphers is about. But those results to date have been cryptanalyzed. So that's Monkey in a nutshell. Looks like I'll have enough time to touch on Black Rugose. So Black Rugose is really based on a few observations. The first of which is, hey, everyone knows DES is not really trustworthy anymore. We're moving towards larger block sizes, 128 bits, 192 bits, 256 bits. So the real idea, our starting point was basically saying, let's assume we can attack a block cipher with a larger block size. So we have more elbow room to leak bits since the output is larger. And so the idea there is, okay, suppose that a sufficient number of plain texts are redundant, streams of zeros, streams of ones, whatever it is, and can be compressed using, say, Huffman compression. Can we fabricate a channel to leak key bits and hopefully achieve even better confidentiality with respect to the reverse engineer? And the idea is, yes, you can do this. So basically, in this design, we use 192-bit block size, and 192-bit key size. And when the plain text can be compressed to 96 bits or less, it is. We also produce a small Huffman tree, and we concatenate those together, and when we encrypt that. And then the idea is to somehow leak two things in the remaining space. One, a secure encryption of bits of the symmetric key that we're trying to learn, that the designer's trying to learn. Okay, so we want to leak m bits of the deterministic asymmetric ciphertext in the remaining space. We also need to have some way to allow the decryption algorithm to disambiguate between when the encryption algorithm was able to compress plain text and when it wasn't. So there's kind of an if statement embedded in Black Rugos. If it doesn't compress, simply encrypt it. If it compresses, compress it, create the tree, leak the bits, and somehow enable it to disambiguate. And the way that we allow that to happen is we actually put a checksum. There's a checksum field in the block that allows the decryption algorithm to know with overwhelming probability whether or not the input plain text has high entropy or not. So here's a quick overview of the Black Rugos cipher. The goal is to leak this 192-bit key to the malicious designer. It leaks m pseudo-randomly selected bits from the deterministic asymmetric ciphertext in each output. And again, this was the paper where we had made the observation of the coupon collectors problem. So basically, the first thing that the encryption algorithm does, this is kind of interesting, is it measures the entropy of the input. The encryption algorithm checks whether or not it can compress the plain text. If it can't, it encrypts it using a particular block cipher internally. If it can, if it does compress to 96 bits or less, it encrypts the compressed string along with the Huffman tree that's needed to reconstruct it. Again, this uses pseudo-random functions just like Monkey. M bit positions from the deterministic asymmetric ciphertext are selected randomly, and those bits are leaked. However, this isn't a 3-operand XOR now. This is a 2-operand XOR. It's an XOR of the pad with the asymmetric ciphertext bits. So that's how we leak the M bits in there, and then we also have to add to this checksum field. And so it's quite a bit different. We've created space. We've literally fabricated space here. So that's why it's this 2-operand XOR. Okay. The security of Black Rugos. I'll give you a quick 10,000-foot view of the security. Basically, what happens in Black Rugos is we leak a bound, either upper or lower, on the plain text to the reverse engineer. And because of this checksum field, we have to make sure that indistinguishability still holds against the end user. And for this, sort of the intuition here is that the plain text space is so huge, you're not going to be able to encrypt them all and check to see for failure. Because the interesting thing about this cipher is, with negligible probability, the checksum field will match under the hash for a plain text that wasn't compressible. So what's interesting is, even though this is purely deterministic, there is a non-zero probability that decryption will fail. So, so this is an improvement over monkey. It's not perfect, but instead of leaking a single bit, we do leak a bound on the ciphertext. We'll know it either compresses to 96 bits or not. So I need to wrap up my talk. I had a feeling I wasn't going to get to the selected areas of crypto one. So in conclusion, we reviewed the history of backdoors and the early concern of backdoors by the federal government. We explained some of the controversy over DES and DSA, and we showed approaches that the research community uses to cast doubt on designs. And finally, we showed two cipher designs, Monkey and Black Rugos, that enable the secure and subliminal leakage of symmetric keys. So I have time for questions. Yes?
What did you say setup stood for?
Secretly embedded trapdoor with universal protection. So that was a Crypto 96 paper I did with Modi, where we built a backdoor into RSA key generation. We've adapted that notion to building backdoors into block ciphers. Yes? To date, well, we implemented some of the backdoors against public key crypto systems like the RSA key generation. We have not implemented Monkey or Black Rugos or Insignis. We're well aware of the slowdown for doing public key operations when you do block encryption. These are still very theoretical type of, at the theory level of results, plausibility results. Does that answer your question? I would envision, if this were ever done in practice, that it's stream ciphers that would give you all the plain text ciphertext pairs. The IV is usually public, right? And so if you look at the different possible modes, output feedback, cipher feedback, CBC, all that, you'll see that some of these will actually give you an incredible number of pairs if the file is large enough. So it is compatible with certain operating modes. Yes?
Now, these are secret designs, so if you could look at the design, you see the backdoor. Right?
Absolutely. In these, not in Richmond and Pernille and Patarin and Goubon tried to solve that problem.
And have you done any work on backdoors in public key ciphers?
Yes, we have a backdoor in RSA key generation. We have a backdoor in DSA and discrete logarithm-based digital signature schemes. There's an interesting backdoor in El Gamal when you do hybrid encryption, not electronic code book encryption, but hybrid encryption. There's actually quite a bit. And it's ongoing work. Next month at Queen's University, I'm presenting a brand new backdoor in RSA key generation. So this work continues. Okay, I need to stop. If anyone has any questions for me, I'd be very happy to answer them down on the floor. Thank you very much.